All right, so for the next section here in Unit 7, we're going to be talking about inverse trig functions. Now, functions are great in that we can put in a value and then get a single value back out. Remember, that's part of the definition. It's, for every x there is one and only one y. We test that with the vertical line test and things like that. But then we also know that we've got inverses of functions which have to be one-to-one, which means they have to pass the vertical line test, and then they have to pass the horizontal line test, so that when we take the inverse, that inverse will be a function as well. Well, if you think about trig functions and their periodic behavior, that's not going to be something that's going to be easy to do with trig functions. Unless you specifically limit the domain in some way, you're not going to have an inverse that is also a function of an inverse of the trig functions that is also a function. So that's kind of what we're talking about with this section. Inverse trig functions. For inverse trig functions, you're going to input the ratios. In other words, the sine and the cosine values that you get out. The ratios of the sides of those triangles that we use to make our sine and cosine values. And what's going to happen is the output is going to be angles. So you're going to input a trig value, and it's going to tell you what angle that applies for. Since trig functions are periodic, which means they have many, many repeated outputs, we must restrict their domain to an interval on which they are one-to-one in order to define their inverse as a function as well. So our limitations for this are, if we're dealing with the inverse sine of x, that's sine to the -1 of x, or also said as arc sine. These are the same thing. They're just two different ways of notating it. Sine to the -1 of x, that is not the reciprocal. The same way we did with f to the -1 is not the reciprocal. That's the way of writing the inverse. Same thing with the trig functions. So sine to the -1 of x or arc sine of x are representing the inverse sine of x. It has a domain, a value that you can put into it from -1 to 1. If you put anything outside that domain, if you grab a calculator and try to do the arc sine or the inverse sine of 2, it's going to give you a domain error. If it says if ever the calculator tells you domain error, you're putting in a number that it cannot find the value for. In other words, you're picking something that is outside the domain of the function that you're plugging it into. All right, now the range on this is from -pi/2 to pi/2. Now, it's from -pi/2 to pi/2 because that's the area that we have to limit the sine function to where it is 1-to-1. So let me sketch the sine function for you here. Remember, we start at 0, we go up to the maximum, down to the minimum, or down to midline, down to the minimum, back up there. So there is one period of the sine function. And as we can see right there, if we draw horizontal lines, if we use this period, then that's not going to be enough to limit it down to being 1-to-1. So what we do is we actually go backwards to -pi/2, and that takes us down here to the minimum, and we limit the domain. We limit the domain of the sine function, the original function, from -pi/2 to pi/2, and that gets us something that's going to pass the vertical line test. It's also going to pass the horizontal line test. So that means that we're going to be okay with this having an inverse, and that inverse would also be a function. So that's where we get the limitations here. What's our minimum value right there? Well, that is -1. Our maximum value here is at the top, it's +1. And then where is this? Well, that's -pi/2, And where's this? That is at positive pi over 2. So when we limit it that way, we've got something that's 1 to 1, and when we take its inverse, remember inverse, the domain and the range swap. So now we go from a range of negative 1 to 1 to a domain of negative 1 to 1. We go from a domain from negative pi over 2 to pi over 2 to a range of negative pi over 2 to pi over 2. This is all the properties of the inverse sign. But that's why and how this works. Now, we're going to have exactly the same thing for the inverse cosine and the inverse tangent. I'll show you the inverse cosine, and the tangent, well, it's pretty self-explanatory. If you remember the last section, we drew the inverse tangent, and the inverse tangent looks like this, going from negative pi over 2 to pi over 2. That's why we have a range of negative pi over 2 to pi over 2. We only take the first period of the tangent function, the first block. Because remember, we've got vertical asymptotes here and here, and that's all we do. We just take that first set between negative pi over 2 and pi over 2, and that gives us something that's 1 to 1, and we can do the inverse. That's also going to be a function there as well. All right, so real quick, let's look at the cosine. And remember, with cosine, we're going to start up here at positive 1, go to the midpoint, go to the minimum, go to the midline, go to the maximum. So the actual curve looks like this and continues on over and over and over again. So if we look at that, we can limit ourselves from 0 to pi right there, and we have something that's going to be very similar to this one. It's going to be 1 to 1. It's going to pass the vertical line test and the horizontal line test, so the inverse would be a function. So that's where we get our limitations of the domain. We limit the domain here, which becomes the range of the actual inverse trig function. And once again, we get positive 1 down to negative 1, and that becomes our domain for our inverse. So that's where those come from. So the easy thing is this. Just remember, when you take the inverse sine of an angle, let's say we had y equals the inverse sine of 1/2. We're looking for where the sine is 1/2, but it has to be in this range of values. We cannot put something like a 3 pi over 2 because the 3 pi over 2 is not in this range. We can't put pi. Pi is not in this range. We have to come up with an angle that's in that range right there that's going to give us, that if we plugged it into the sine function, would give us a sine value of 1/2. So this is where knowing that unit circle becomes really, really, really important. Because if you know the sine of 1/2, or you know what angles give you a sine of 1/2, it's a lot easier to think backwards and find what the angle that you came from should be, especially if we're limited to be between these 2 points. All right, number 1, evaluate each expression or explain why it is not possible. All right, so looking at A, remember what we're doing when we take the arc sine. If we're looking for arc sine of negative square root of 2 over 2, what we're really asking, remember how those inverses are, and we could go back and do it. And we can rearrange this and think about it in the backwards way. We are literally asking the sine of theta equals negative square root of 2 over 2. But the only problem with our theta here is it's got to be between negative pi over 2 and pi over 2. So that's really what we're asking when we are trying to solve this. We're saying, what angle would I need to plug in here to get a sine value of square root of 2 over 2 but it has to be in between these two angles right here. Now, we know all of our square root of 2 over 2's are going to be a pi over 4. The only pi over 4's are going to be positive, single pi over 4's. Not a 3 pi over 4, a 5 pi over 4, any of that. Those are not going to fall in this range. So now we know it's pi over 4, but which one's going to give us a negative? Well, if we had the sign of positive pi over 4, that's going to give us a positive square root of 2 over 2. But remember, we're dealing with from here to there, quadrants 4 and 1, and quadrant 4 down here, we're going to have a sign value, a y value, that's negative. So it's going to be negative pi over 4. And guys, that's really all there is to it. If you know your unit circle, it's real easy to play backwards. This one's a little more complicated here. This one, we've got to figure out what ratio gives us negative square root of 3 over 3. And guys, the only way you're going to do that is just repeated seeing it over and over and over again. Remember, one of these gives us 1 over the square root of 3, and the other one just gives us the square root of 3 over 1. Now, the way we get the 1 over the square root of 3, if you remember, it means that we have to have a 1/2 on top and a square root of 3 over 2 on the bottom. And then keep, change, flip, and we get 1 over square root of 3, and then have to rationalize our denominator. So now, we're thinking through this, so that means my sign value has to be that, and my cosine value has to be square root of 3 over 2. Now, because our tangent value is negative, that means one of these has to be negative and the other one has to be positive. That's going to occur in quadrant 4. And remember, tangent also has the exact same limitations as we had with sine. So now, let's break this down and see what we've got. So remember, we're literally asking the tangent of what angle is going to give me negative square root of 3 over 3, or negative 1 over the square root of 3 if it's not rationalized. Those are the same value, and which means that it's going to give me a 1/2 on top and a square root of 3 over 2 on bottom. Now think about quadrant 4. For quadrants 1 and 4, x values are always positive. Always, always, always. There's nothing here that's going to make that bottom a negative. So that means we're looking for where the top is negative. Because remember, cosine is our x value. And in these two quadrants that we're dealing with here, both of those are going to give us positive cosine values. So only negative can be the sign. That means it's going to be down here in quadrant 4. What angle am I looking for? Well, remember, if I've got a cosine value of square root of 3 over 2, that means it's a pi over 6. What's the only negative pi over 6 that I've got down here? Well, that means theta is going to be negative 1 pi over 6. Remember, you're not doing the 2 pi over 6 because that's pi over 3. All right, and then we get over here to the last one, the arc cosine of 3 pi. This looks so official and so awesome and all that. There's only one problem. Remember, what are the only values that we can plug into this thing? Into the arc cosine or the arc sine. We can only put in values that are between -1 and 1. If we put in values outside of that, this thing does not exist. Or in this case, they told us not possible. So write down not possible, and they want to know why. 3 pi is outside the domain of arc cosine. Which is, if you just want to go ahead and put some extra oomph in it, -1 to 1. So since 3 pi is 3 times 3.14159, it's definitely going to be larger than 1. So it's going to be 9 point something. So you need to make sure that you understand that and know why. Just because it looks really nice, and it does. I mean, you see that pi in there, you automatically think, hey, that's got to be able to be done. No, it doesn't. All right, so determine if each statement is true or false and give a reason for your answer. All right, so for number 2, we have the arc sine of 5 pi over 6, and it's equal 5 pi over 6. All right, this one is false. Now, can you tell me why? Well, here's the thing. If you don't recognize it, where is 5 pi over 6? Remember where arc sine, remember when we get arc sine, we can only have angles come out that are between negative pi over 2 and pi over 2. Well, 5 pi over 6 is definitely larger than pi over 2. 5/6 is more than 1/2 if you just kind of ignore the pi's there for a second. So false, since 5 pi over 6 is outside the range of arc sine. All right, and then look over here on this one. We do the inverse cosine of negative square root of 2 over 2. Then we take the cosine of whatever angle. And guys, here's the way you need to think about this. This is going to give you an angle in here. You're going to have some theta. If I then turn around and take the cosine of that same theta, am I going to get the same thing back? Yes, and the reason why is because I am not limited here. I'm going to be limited here. I'm going to be limited on the angle that I can get out. Now, it may not be the same angle that they originally used to get this value, but it's going to be, when we take this angle, it's going to be an angle between 0 and pi. Always, 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 because of the definition and the limitations of the inverse cosine. Now, it's going to also definitely be an angle that's going to give me a negative square root of 2 over 2 for a cosine value. So when I get the angle that I get out of this and then take the cosine, I'm going to get that value right back. The problem we run into is one over here, where we take the sine, and this is going to give us a ratio. That's going to give us a sine ratio. Well, just because we've got that sine ratio does not mean when we take the arc sine of that ratio, square root of 3 over 2, 1/2, whatever. This one's going to be 1/2 in there, right? It's going to be 1/2, and then we're looking for the arc sine of 1/2, and it's going to be pi over 6. It's not going to be 5 pi over 6 because of the limitations that we're putting on arc sine and arc cosine and arc tangent. They are limited in what angles that they can give back. 5 pi over 6 is not in that limitation. Over here, we've already taken that limitation when we find this theta in here. So then when we take the cosine, we're just going to get the same value for that angle it is. Because remember, it's just a coterminal angle. No, sorry, it's not a coterminal angle, but it's a terminal angle that's going to give us the exact same y value, or x value in this case for cosine, that the original one would give us. All right, so how many values of x will satisfy the equation tan x equals -1? Well, remember, tangent of x is equal to sine x over cosine x. And for that to be -1, we would have to have a negative on top or bottom, but not both. So where does all that occur? Well, that's going to give us an x value of 3 pi over 4. Not 5 pi over 4, but 7 pi over 4. And then back around, that would be 11 pi over 4. And then 15 pi over 4. And we can do this forever. Because remember, all we're really doing is we're going to list the 2 times that it happens, 3 pi over 4 plus, and it's going to happen every pi, so we can end up doing k pi x. That's not real good, is it? K pi x, and that lists every single one of them. So infinitely many. Now, how many values of x satisfy the equation inverse tangent of -1 equals x? Well, remember, tangent x, we're still limited to that. That's an awful drawing. Oh, that's even worse. That's going to have to do. So we're still dealing with just from -pi over 2 to pi over 2. And there's only one value in there that's going to give us -1. That's going to be at -pi over 4. So in this case, x would equal pi over 4, so there is only one, and it's because of the limited domain that we have to put on the original tangent function for it to be 1-to-1. All right, so number 4, let f of theta equal cosine theta if AB is on the graph, so that's a point, is on the graph of f, and BA is on the graph of f inverse, which of the following statements is false? All right, so what we're looking for is, so f, let's write some of this stuff out. F of theta equals cosine theta. And what do we know about that? Well, for this, remember our domain is all real numbers. Our range is from -1 to 1. And it's got a period of 2 pi. Now, when we talk about the inverse, now, here's the thing. If AB is on the graph, what this is really saying is the cosine of A equals B. Input value, output value. And when we put the inverse over here, that means the cosine of B equals A. Remember, that's just what, inverse cosine of B equals A, because of the reversing effect of an inverse function. So now, if we know that we've got the graph of f, and BA is on the graph of the inverse, which of the following statements is false? So we're looking for one that does not apply. Now, it may help to kind of see these graphs. So remember, cosine, we've got this. Right there. It does continue on. And then when we talk about the inverse we're going to come down here to, this is at -1, but we're actually going to go down to, we're going to go from 0 up to pi. All right, so when we graph the inverse cosine, we're actually going to come over here to 1. And remember, right here we're at pi over 2, so that's roughly about 1.57. So we're going to start about right here, and it's going to look like this. It's going to go up to pi. That's actually not that great. It's going to go more like this. So now, if we've got B and A on the graph of, so that means that we've got a limitation here. What do we know? We know the values that we can put into this to be cosine are unlimited. But once we get over here, we know our output has to be from -pi/2, for cosine, 0 to pi. And then our B value, the value that we're getting out, remember our trig functions are always going to be from -1 to 1. And that's going to be true on both of these. All right, so looking at our things here, we know that A is going to be between -1 and 1. Yep, that's true. And we're looking for the one that's false. A is going to be between 0 and pi. Well, remember, we're limited to 0 and pi over here when we take the inverse cosine function. And if the same exact point, or the same exact values are on both these, then A has to have the same limitations as it has over here. So yeah, that's going to be true as well. All right, and B, comma, A plus 2 pi is also on the graph of F inverse. That's going to be false. Now, why is that going to be false? Well, that's going to be false because, remember, we're limited on our A from 0 to pi. So let's say we took in the middle and said pi over 2. And then we add 2 pi to it. That's going to be larger than pi. So that means it's not going to be able to be on the graph of F inverse. So this one is the false one. And then just to check, let's see, -AB is also on the graph of F. Hey, guess what? This one's going to be true as well. Now, here's the question. Why? It's something we've been talking about in class on multiple occasions. It's because cosine is an even function. So remember, we've got B is equal to cosine A right there. So what happens on an even function if I put a negative value in there? Well, with an even function, I get back the exact same value I would have gotten if I plugged in a positive value. So if B equals cosine A and cosine A is an even function, then cosine negative A is also going to give me B. So that's going to be true as well. So this is the one that's false. Definitely, definitely, definitely.